So today we are going to be talking about some things that are actually going to make your life a lot easier. So far when we've found the derivative of a function, we've always been using this limit definition. And hopefully you understand kind of where that limit definition came from. And in every calculus class, you kind of start out with this idea of like doing it kind of the long way and really understanding the idea of a derivative and where it comes from. However, it's not really practical to always use that limit definition. And so what we're going to start learning basically from here for essentially the rest of the course, we're going to be learning other rules that let us take derivatives for specific types of functions. So one thing just to pay attention to is as we learn these new derivative rules, just make sure you're paying attention, like for example, on a quiz or a test or on the homework, to which method is being asked for you. So if a question asks you to use the limit definition of the derivative, you do still need to know how to do that. But otherwise, you can assume that you can use basically these derivative rules that we'll be talking about today and other days in the future. Okay, so we are in section 3.1. And so today we're going to learn a derivative rule that is called the power rule. So we're essentially going to learn how to take the derivative of any function that's of the form x raised to a power. And then we'll also learn another rule that will help us work with other types of derivatives. So I want to remind ourselves first of some of the derivatives that we've already found in previous videos. So I'm just going to make a little table here. So for example, in the very first video that we did about the derivative, we found that the derivative of x squared came out to be 2x. So I don't necessarily expect you to remember that, but if you wanted to, you could go back, watch that video, you would see that. And actually, we'll do this one with limits because I think it's a good example to see where the rule comes from. And then in, I think it was yesterday's video, we did x cubed, and that came out to be 3x squared. So one thing that you might notice here is that basically the number that ends up being the coefficient, so when I say coefficient, that's like this number, and maybe let me even color code this. So this number here is the same as the original exponent. So the exponent of the original function became the coefficient of the derivative. And then similarly here you had an x cubed, and that became 3x squared. Oops. So something else you might notice is that if you look at the exponents on the derivatives, they are 1 less than the exponents on the original function. So you wouldn't necessarily write 2x to the 1, but it is, right? X is the same thing as x to the 1. So the original exponent was 2 and it became 1. Here the original exponent was 3 and it became 2. And so the general pattern is going to be, I'll put kind of like a dot, 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 because I want to put one more example on here. So if you have a function where it's x to the n, the derivative is always going to be n times x to the n minus 1. So the way that I kind of visualize it is you're like taking that exponent and you're bringing it down in front, and then you're subtracting 1 from the exponent. So just to give like one other example, x to the 4th, that would be 4x cubed would be the derivative of that. So that's the rule, and we'll write that out more formally in a little bit and see some more examples. I want to give you some idea of why that rule is the way it is. So this is going to be a little bit technical. It's not super duper important, but I just think it's interesting, and I just, as a teacher, I just really don't like to tell you rules without giving you some intuition of where they come from. So that's why I'm going to go through this. So basically, why does the derivative of, if you have a function f of x equals x to the n, come out to be f prime of x is equal to n x to the n minus 1. So I want to write out the the limit definition for x squared and kind of see where that 2x comes from. And then we'll look at also x cubed and x to the fourth, and we won't do the whole process, but we'll just kind of try to see again, like where it's coming, where the derivative part is going to come from. So for example, if we're doing f of x is equal to, maybe let me actually write this down here. So if you're doing f of x is equal to x squared, we know that the derivative will look like this. The limit as h approaches 0 of f of x plus h, so that's going to be x plus h squared minus, minus x squared. Sorry, it always takes me a moment to find the eraser button on my pen. All divided by h. So if you multiply out x plus h squared, you're going to get x squared plus 2xh plus h squared minus x squared over h. And so one thing that you notice right away is that the x squareds are going to cancel out. So those are not going to be a part of the derivative at all, right? Because those just go away. And then what are we left with? Well, we're left with the limit as h approaches 0 of 2xh plus h squared over h. Then we can cancel out some h's. And so we're left with the limit as h approaches 0 of 2x plus h, which that when we plug in 0 for h, we're just left with 2x. So that's where the derivative being 2x comes from. So let's kind of work backwards and look back along this track of taking the derivative and see like where did that 2x appear. So if we look back to the second step, so right here, notice that the 2x came from this part where it's 2x times h. And so why is it that that was the part that gave us the derivative? Well, it's because that's the part that had exactly one h in it, right? Because the part that had no h's, the part that was just x squared, they have no h's in them at all. They're just going to cancel out, and they have to cancel out because we know in order for this to simplify, everything has to have an h in it that we can then cancel and do the simplification. So anything that did not have an h in it is going to cancel out. And then this h squared, well, that doesn't cancel out, but what ended up happening is because it was h squared, when we divided by h, we were still left with an h. Does that make sense? So we started with h squared, we canceled out the square part, and then we were still left with an h. And so if you're still left with an h, then when you plug in 0, that part is also going to go away. So basically, what I'm getting at here is that the only part of, if you look at basically this part of the limit, the numerator, the only part of that is going to contribute to the derivative is the part that has exactly one h connected to it. Because if it has exactly one h, that h will perfectly cancel out and you'll be left with something that just has an x in it. So let me just kind of write that down. So this is the term that contains exactly one h. So not h squared, not h cubed. We'll see in some later examples that there might be ones that have different powers of h. We want the one that has exactly one h. Okay, so I want to look at now x cubed. And so I'm not going to write out the entire limit. I just want to think about basically this part, what's going on in the numerator, because that's enough to kind of help us figure out what will be left over after you go through all the cancellations. So if you look at what the numerator comes out to be, so maybe I'll just write that down so that if you look back at this as notes, you won't think that that's the whole thing. So the numerator of the limit is going to be x plus h cubed minus x, I keep writing h for some reason, minus x cubed. So once again, we know that like the x cubed is going to cancel out. And so let's think about what actually will show up if you take x plus h cubed and multiply that out. So x plus h cubed is the same thing as x plus h times x plus h times x plus h. So one way of multiplying this is what I did in the other video. So in the video from yesterday, when I multiplied this together, I actually multiplied these two together first, and then I multiplied in the x plus h. And so that's one way of multiplying three things together. But there's actually another way that I think will kind of make it a little bit clear what's going on here. So one way of multiplying things together like this is basically going through and picking one item from each set of parentheses. So for example, if I pick x, x, and x, 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 and x, that will give me x cubed. Or if I pick, let's say, x, h, if I pick x, h, and h, then I would have x times h squared. Or if I pick h times h times h, I would have h cubed. So all of those different possibilities of what you could get by picking one item from each of these gives you another term in that product. So I'd encourage you, if you're interested, go back to yesterday's video where we wrote out what that whole multiplication is, because I'm not going to do that. I'm not going to write everything out. But if you go back to that video, you'll see that you could figure out those terms just by kind of picking items out of each of these. So we want to see how we could get items that have exactly one h in them, right? Because that's the part that's going to survive the limit. So one way we could do that is we could do x times h. So that would give us x squared h. There's another way we could do it. We could do x times h times x. And so that would give us another x squared times h, right? Because you have two x's and an h. Another way we could do it is we could do, let's see, we've already done this h, that h, so we could do h times x times x. So altogether that would be, that would be another x squared times h. And so altogether that would give us 3x squared times h. So that would be the part that would survive in the numerator. So similarly to how up here it circled in purple, the 2xh was the part that survived. After we went through all the limit stuff, we were left with 2x, and that 2x came from this 2xh. Similarly here, if you go through and you kind of set up the limit again, you would see that the only part that's going to survive after you do the cancellation and after you plug in 0 for h, the only thing that will be left over will be this 3x squared. So just to kind of show one more example of how that works out. So let's say now that we're looking at x to the fourth. So again, I'm just going to write the numerator, x plus h to the fourth minus x to the fourth. So if we multiply out x plus h to the fourth, now we're multiplying four things together. So again, if we did that same process, now we're looking for things that have only one h. That would be x times x times x times h. So that would give us 1 x cubed h. We could also do x times h times x times x. So it would give us another x cubed times h. We could also do this x times, let's see, so I'm trying to pick which one is h, so I guess, I don't think I did this in the most organized pattern. So let's see, x, x, let's pick this h, and then this x, so that would be another x cubed times h. And then we could also do this h, this x, this x, this x. So basically going through and finding all the different ways that you could end up with only one h, and so that means all the rest of them have to be x's. And so this would come out to be now 4x cubed h. And so again, if you go through that whole limit process, the part that will be left over is going to be exactly the 4x cubed part. So if you found this confusing, that's okay. I know this was very different. It's not very important that you understand this. It was just, I think, again, I just wanted to kind of give you some idea of where this rule comes from. You definitely don't need to understand what we just did in order to use the rule. So I just want to make sure I'm distinguishing between that. And that will happen frequently in this class, where I will give you a proof or kind of an explanation of where something comes from. And, you know, I do that for your benefit, but if you don't totally follow it, that doesn't mean that you're not going to be able to use the rule, right? You can, like, being able to use the rule is separate from understanding completely where the rule comes from. Okay, so let me write out formally what we basically just introduced on the last page. So this is what's called the power rule. So I'm going to introduce a little bit of new notation. And we're going to actually be using this a lot because we're going to be introducing all of these new derivative rules. So if I write something that looks like this, d over dx, that literally means the derivative of. And we'll actually get more into talking about this notation in tomorrow's video. So for now, I don't want you to worry too much about it. Just know that it's a way of writing the derivative of. It's basically like if you want to say the derivative of something, but you don't want to have to write f of x is equal to f prime of x is equal to, it's kind of a shortcut. So the derivative of x to the n is always going to be equal to n times x to the n minus 1. So that's the same rule that we wrote on the previous page. So let's do a couple of examples. So let's say that you have the function f of x is equal to x to the 100. So what does this new rule tell us? It tells us that the derivative would be 100x to the 99. So this is exactly like the kind of place where it's like really nice that we have this rule that we don't need to use the limits anymore, because if you had to use the limit definition to do this, that would, I don't even think you could complete that. Like that would be x to 100, you'd have to multiply 100 things together. That would take a very, very, very long time. Okay, another example, and this is actually kind of an important example. So let's say that you have f of x is equal to just x. So we kind of already know what the derivative is of just x, right? So x, if you have the function f of x is equal to x, that's a line with a slope of 1 through 0, 0, right? So we know from last time's video that the derivative of linear functions is just the slope. So the derivative should be equal to 1. And it turns out that you still get 1 if you use this rule. So we can use this rule and we can write this as x to the 1. And so how would this rule work? You would bring down the 1, and then you would have x to the 1 minus 1, which is 0. And remember that anything raised to the 0 is 1, so we would get 1. So maybe let me put a note here that basically I'm showing this to you because I wanted you to see that the power rule does still work for linear functions. However, I wouldn't do it like this. I would just remember the fact that if you have a line, the derivative is just the slope. So I'll just say that. Or just remember that the derivative of a linear function is its slope. Okay, so what's really interesting about the power rule, and this, all the examples we did on the previous page where I was showing you, where does this rule come from, those were all x to a power that is a whole number, right? X squared, x cubed, now we did x to the 100, x to the first. But this rule actually works for any power of x. So let's say you had, and let me maybe write that out. So this rule works even when the power n is not a whole number. So for example, and I want to do like a kind of a handful of examples here. So let's say you had f of x is equal to x to the 0.3. Well, you could apply the rule the exact same way that we did above. You could say f prime of x is equal to, we bring down the 0.3, then we have x, and then we would do 0.3 minus 1. So 0.3 minus 1, I'll write that out first, and then we can actually do that subtraction. So 0.3 minus 1 would be negative 0.7. So before we get into our next two examples, I think actually, let me go on a separate page and remind you of a couple of exponent rules that I think will be useful to know. So review. So these are things that you should have learned in your pre-calculus class. So hopefully this, maybe it's a little bit of a review, but hopefully these are things that you have seen before. So basically there's just a few that I'm going to write down here. So one of them is that if you have a number raised to a negative power, that's the same thing as 1 over that number to a positive power. So like x to the negative 2 is the same thing as 1 over x squared, for example. Another one that's good to know is that if you have x to the m over n, that is the nth root of x to the m. Or you could also do it as the nth root of x all raised to the m. Either of those is fine. The first one is the way that people more typically will write it, but they're equivalent. You would get the same answer either way. Another couple rules that are good to know, actually probably just one more that I'll give you right now, which is that if you have if you have the same base being multiplied with itself, you can add those powers. So that would be x to the m plus n. Where does that come from? Just think about what it means. So for example, let's say you had x squared times x cubed. That means you would have x times x times x times x times x. So you would have 5 x's altogether. So think of the exponent as telling you how many of those x's are you actually multiplying together. And so if you're multiplying a few of them here and a few more here, then you add them up to find how many you have total. Similarly, if you have something like x to the n over x to the m, then you can subtract. So that's not all the exponent rules that are out there, but I think those are really the most important ones and the ones that are probably going to come up in today's video. Okay, so with that in mind, let's look at some more examples. So let's say that we had the function, and today's video, by the way, is just going to be a lot of examples. So yeah, I don't know if that's a good thing or a bad thing for you, but just so you know. So let's say that we have, maybe let me call the function something else. Let's call it g of x. So let's say we have g of x is equal to 1 over x. So you can use the power rule on this. So maybe to be clear, and we'll get to this later, the way you would use the power rule on this, you could not just go in and take the derivative of the x part by itself. In order to use this rule, your function literally needs to look like x to a power. It can't be 1 over x to a power. It can't be, something like x squared divided by something by square root of x. It needs to literally be x to a power. And so what that means is that if you have something like 1 over x, you want to find a way to rewrite it so that it is x to a power. So the first step is that we're going to rewrite in x to the n form. So to be clear, we're not taking a derivative right now. All we're doing is taking this function and finding a different way to write it equivalently. And again, I'm calling it f of x when it's supposed to be g of x. So 1 over x, based on the rules that we just talked about on the past page, that's the same thing as x to the negative 1. So once you have it in that new form, now you can use the power rule. So we can bring down this exponent of negative 1 and then write it as negative 1 x to the negative 2. So regardless of whether that exponent is positive or negative, regardless of whether it's a whole number or not, you're always doing the same thing. You're always bringing that exponent down to become the coefficient and then subtracting 1 from the exponent. So if the original exponent is negative 1, the new exponent is negative 2. So this is fine as an answer, but in some cases you might want to be able to rewrite it without negative exponents. So for example, I know on your online homework, they ask on some questions for you to rewrite it without any negative exponents. So basically all that means is to kind of use the same rule that you used here, but just in the other direction. So now we have x to the negative 2, so now we can rewrite this as negative 1 over x squared. So that's one way we can use it, is when we have like 1 over x to a power. So let's see one more kind of secret way or surprise way we can use this. So let's say we have the function h of x is equal to square root of x. So again, this at first glance might not seem like a power rule problem, but it is, because we can rewrite this as x to a power. So how do you rewrite square root of x as x to a power? As we saw on the previous page, anytime you have a root, you can rewrite it as a fractional power. So in this case, it would be 1/2. And so how do we find the derivative? Now we can just use the power rule same way as we did on the other one. So we can bring down the 1/2 as our exponent, or sorry, as our coefficient. And then our new exponent is going to be 1/2 minus 1. So by the way, you are definitely going to need to have some comfort with fractions in this section, because there's going to be a lot of adding and subtracting of fractions going on. And I really, by the way, I would really prefer, and in some cases might actually take off points if you start writing things as decimals. So I want to see when you're dealing with exponents. I mean, so I gave you an example where I actually started with a decimal as an exponent, and that's fine. If the problem is given to you as a decimal, leave it in decimal form. That's fine. If the problem is given to you with fractions, you want to continue to use fractions. So I wouldn't want to see you writing 0.5. I want to see 1/2. So what do we get when we do 1/2 minus 1? Well, that's going to be negative 1/2. So again, like I said on the previous one, this is fine. This is the correct answer, but there might be some cases where you want to be able to rewrite this without using the negative exponent and even without using the fractional exponent. So let's kind of do this in stages. So how would we rewrite this without the negative? We could say 1 over 2 x to the 1/2. And maybe even just write out one more step if you're kind of confused where that came from. So we could rewrite this instead as 1/2 times 1 over x to the 1/2, right? Because we know that x to a negative power is the same thing as 1 over x to the positive power. And then we can combine these and write it as, because multiplying two fractions, you just multiply numerator times numerator, denominator times denominator. And then the last step we can do is rewrite the x to the 1/2 again as a square root. So by the way, these are both, so this one, square root of x, and 1 over x, these are ones that we actually did with limits back earlier in the week. So if you go back and look at what you got using limits, you got the exact same thing. So it's kind of good confirmation that this rule makes sense and it's consistent with everything we've seen before. Okay, so there's just a couple more rules I want to introduce that will allow us to kind of expand the types of functions that we are allowed to take derivatives of without using limits now. So 2 more derivative rules. Oops. So the first one is, let's say you're trying to take the derivative of 2 different things added together. So let's say like square root of x plus 1 over x, 2 kind of distinct functions. So again, I'm using that d over dx notation as a way of writing the derivative of, is how you would read that if you're reading it out loud. So it turns out it kind of just works as you would hope it would. So if you're trying to take the derivative of 2 different functions added up, you can instead just take the derivative of each function separately. So I'll write that as f prime of x plus g prime of x. So by the way, when we write out rules like this, I think one thing that's a really good thing to kind of practice yourself is rather than looking at this and just seeing a bunch of symbols, try to like translate it into something that makes sense to you. So I will always try to do that when I'm saying them. So I would think of this as saying, if you're taking the derivative of 2 functions added together, you can instead take the derivative of the first function and the derivative of the second function and add them together, is the way that I would kind of translate this into plain English. On a similar note, the derivative of functions subtracted, same deal. So if you have two functions subtracted, you can take their derivatives separately. So why is this? Basically, if you write down the limit definition, and I'm not going to do this just for the sake of the length of this video, but if you were to write out the limit definition of the derivative with two functions being added together, you could see that you could split it into two limits. And one of those limits would be the derivative of one function, and the other limit would be the derivative of the other function. So these rules are actually kind of come directly from the fact that limits work in a way where you can split them up over addition. Another rule is that if you are taking the derivative of a constant times a function, what you can do is you can take the derivative of the function normally and then multiply it with the constant afterwards. So I want to kind of show you an example that will maybe explain why that rule works the way it does. So let's look at the graphs of the functions. So the one that is in black is x squared, f of x is equal to x squared. And then the one that is in green is 2x squared. So g of x is equal to 2x squared. So if you think back to pre-calculus and you think about what happens when you take a function and you just multiply it by a number. So in this case, we have the original one and then we multiply it by 2 to get the new one. And so if you think about what does that do to the graph, it stretches it vertically by 2. So what that means is that every point on the graph, so for example, on the original graph, we have the point 1, 1. And on the second graph, we have the point 1, 2. So all of the y values have been doubled. So what effect is that going to have? Well, it's going to make the graph twice as steep, right? So like if you were to take the slope of the tangent line at 1 on this graph, and then take the slope of the tangent line at 1 on this graph, you would find that the slope of the tangent line on the green graph would be twice as steep. So that's basically what this, this constant multiple rule is saying, is that whatever you multiply your original function by, it's going to affect the derivative by the same amount. So just to show one other example, if you compare x squared with negative x squared, well, that means that we're taking the original function and multiplying it by -1. And that's going to have the effect of reflecting it over the x-axis. So again, if you compare like all the different derivatives, all the different slopes of the tangent lines on the original function with the ones on the reflected function, they're going to be negatives of each other. So the derivatives will be negatives of each other. So whatever you're multiplying the original function by, you have that same effect on the derivative. And maybe let me just write, for any real number C. Okay, so let's look at some examples of how this actually works. So let's say you wanted to take the derivative of the function f of x is equal to x to the 100 plus 1 over x plus square root of x. So the first rule that we wrote down, this addition rule, tells us that we can actually just take the derivative of each of these things individually. So we already know how to take we already actually did these three, so I'm not going to go through the work for them. So we got 100x to the 99 for the first one. The second one we got negative, so I should subtract 1 over x squared, and then the last one we got 1 over 2 root x. So that would be our derivative. To give another example, so let's say that we had a function g of x, and that function was equal to 10x squared. So if we wanted to take the derivative of this function, we can use this idea of the constant multiplication rule, so the one at the bottom in blue. And it basically tells us that you can focus on taking the derivative of the part that you are, like the power rule part. So focus on taking the derivative of that and then multiply that by 10 at the end. So we know that the derivative of x squared is 2x. And so we say, okay, the derivative of that is 2x, and then we're going to multiply that by 10. And so altogether, we get 20x. And then in a minute, we'll do a few more examples where we're going to kind of pull all of these different rules together and do some slightly more complicated derivatives. But one more thing I want to mention while we're kind of on this topic is a couple of rules that do not exist that I want to make sure everyone knows are not a thing. So it is not true that the derivative of two functions divided by each other, that is not the same as taking the derivative of each of them individually and dividing. It just does not work that way. We'll do this actually next week. There's a special rule for taking derivatives of things divided, and it is way more complicated than, I shouldn't say that. It's not that bad, but it's definitely not just taking the derivative of the numerator and denominator separately. It just doesn't work. We can actually already see an example that doesn't work, right? We know that the derivative of 1 over x is negative 1 over x squared. If you tried to take the derivative of the top and the bottom separately, the derivative of 1 is actually 0, right? Because 1 is like a horizontal line at a height of 1. The derivative of that is 0. And the derivative of x is 1. So you definitely would not get negative 1 over x squared. So I just want to point out that we already have evidence that that rule does not work. And then other one that is not a thing is that it is not true that if you're trying to take the derivative of a product of two functions, that is not the same thing as doing f prime of x times g prime of x. Now, I'm sure that some of you will make those mistakes, and so I will kind of keep telling you, reminding you this over and over, but I just wanted to kind of get it out there for the first time today. Okay, so let's do a couple more slightly complicated examples. And actually, sorry, one more thing I should probably write down that I just kind of mentioned now, and it's something that has come up already, but I just want to kind of write it down officially. So if you're just taking the derivative of a constant on its own, so like f of x is equal to 5 or f of x is equal to negative 2, the derivative of a constant on its own is just equal to 0, always. And the reason for that is that if you think about, what does a constant look like as a graph, it's a horizontal line. So the slope is 0. It has no rate of change. Other functions are changing, right? Constant functions are not changing. So it makes sense that their rate of change is 0. So that does not mean that you multiply by 0. Like in a situation like this one here, notice that you're not taking the derivative of the 10, right? You're leaving 10 on its own. So it's only when you're taking the derivative of a constant kind of as its own item. As soon as you're multiplying a constant with something else, that constant is just going to kind of come along for the ride. It's not going to change. It's just going to stay there. You can think of it as something that's kind of going to scale your derivative. Whereas if you're just taking the derivative on its own of a constant, then it's like, okay, it's just a constant. It's not scaling anything. Its derivative is just 0. All right, so just a few more examples. So let's look at this one. So let's say that f of x is equal to 7x times the square root of x plus 5x cubed minus 4 over square root of x plus 2x minus 1. And let's say we're supposed to take the derivative of this. So first thing is, we know that we're allowed to just take the derivative of each thing that's being added or subtracted. Those we can take the derivative of individually. What else do we have to work with? Well, we see that in some cases we have things like this. We have like 7 times something, we have 5 times something, so we have 2 times something. Those are going to be scalar multiples, so we'll kind of like let those come along for the ride when we take the derivative of those terms. And then the only other rule we really have to work with right now is the power rule. And so that means that we want to rewrite all of this stuff as all just being powers of x. We need it to just be x to a power, x to a power, x to a power, or it could just be a constant. That's the only other thing we know how to take the derivative of. So let's start by rewriting. So again, I just want to really make this clear. Maybe this is obvious, but I've definitely had students be confused about this in the past. When we're rewriting it, we're not taking the derivative yet. We're just doing like algebra. We're taking our equation and we're just finding a new way to write it. Okay, so I'm going to start by taking 7x and square root of x, and we can rewrite that as x times x to the 1/2. And then 5x cubed, that's great. We don't need to do anything about that. 4 over square root of x, so divided by square root of x would mean it's x to the negative 1/2, right? So this can become 4x to the negative 1/2. So the negative is because it's in the denominator, the 1/2 is because it's a square root. And then we have 2x, and then we have minus 1. And then let's do a little bit more simplification. So there's just one thing that we need to do, which is that here we have x times x to the 1/2. We need to combine those to be just 1x to a power, because it would be wrong to, for example, take the derivative of this, take the derivative of that, because remember that you can't multiply derivatives by each other. It doesn't work like that. So we want to simplify this. So x is the same thing as x to the first power. So we want to add those two exponents together. So x to the 1, and then add 1 plus 1/2, and you get 3/2. So now we are ready to take the derivative. And by the way, just another tip, a place where I see students commonly make mistakes is that they will start taking the derivative of some stuff while they're still kind of simplifying other stuff. That I think is really a recipe to get confused. I would really recommend that you, if you're going to do simplification, do the simplification. Don't write f prime of x. Just say, okay, I'm still doing f of x. I'm still doing f of x. Once you're done with all the simplification, then take the derivative. Because I've seen students, for example, maybe they're like, oh, the derivative of -1 is just 0, and they get rid of that. But that's not really part of the simplification. That's part of the derivative, which is a totally different, separate process. Okay, so now let's take the derivative. So what we're going to do is we're going to go through and look at each of these terms individually and take the derivative of each of them. Because they're just connected together by addition and subtraction, we're allowed to do that. So the first one we're going to take the derivative of x to the 3/2, and then we're going to multiply it with 7. So we can kind of just leave the 7 there. It's just kind of coming along for the ride. So the 3/2 is going to come down. That's our new coefficient. And then the new exponent is going to be 3/2 minus 1. So I'll write it like that for now. So we're just subtracting 1 from the exponent, as we always do with the power rule. And we'll come back and simplify this in the next step. So the next part, we have that 5. That's just going to kind of come along for the ride. And then we're going to bring down the 3, and we have 3x squared. Subtract 1 from the old exponent, and we get 2 as our new exponent. Next one, we have -4, and then we're going to multiply that with -1/2, because that's the original exponent. And then our new exponent is going to be -1/2 minus 1. So we're going to have to figure out what that is. Next part, we have 2x. So that one we can actually just think about how if you have a number times x, the derivative is just going to be that number. Basically, it's because 2x is a linear function, and the derivative of a linear function is just a line, it's just the slope. So the derivative of 2x is just 2. And then finally, the derivative of -1, that's 0. So I'm just going to write it down so that you know where that -1 went. Okay, so now let's go through and simplify this. So this one here becomes 21 over 2 x to the, so 3/2 minus 1 is going to give you 1/2. Next we have 5 times 3, so that's 15, x squared. Next we have -4 times -1/2, so that's going to become +2. And then the new exponent is going to be -1/2 minus 1, so that's -3/2. And then we have +2. So this one, maybe let's just leave it, because like I said, it really depends what you're doing, and we'll see this more in the future, but in some situations, it's actually kind of nicer to leave your answer like this. In others, you might want to rewrite it as, we could rewrite this, for example, as the square root of x, and we could put this negative exponent in the denominator, but let's just kind of leave it as it is for now. Okay, so that was our answer. So I just want to do 2 more examples. So first one is going to be one where initially it might seem like we cannot use the rules that we have, but we actually can. So let's start with what you would not do for this one. It would not be correct to take the derivative of the numerator and denominator individually. That would give you a totally, completely wrong answer. And if you're curious, like, why does that not work? Again, just like if you try some examples, you'll just see that it doesn't work. And then we'll get more into this next week when we see how you actually do take derivatives in that situation. So let me just write that down. Do not take the derivative of the numerator and denominator separately. So we'll see that there's a rule, and if you've taken calculus before, you might remember there's something called the quotient rule. So that's one way to do this, but there's actually a way easier way to do it that we already know how to do just based on today. So what can we do? We can rewrite this function, and the way we're going to rewrite it is we're going to split it into 2 fractions. So instead of writing this as all one fraction, we could write it as x squared over x minus square root of x over x, right? Like I think it's an algebra technique that a lot of people kind of forget about. I think we're really used to, if we have something that's like a over c plus b over c, we're like, oh, right, that's a plus b over c. We know how to make a common denominator. But it's also true that if you have 2 things that are already together, you can split them up. There's nothing that, disallows you from doing that. So that's kind of a good algebra trick. That's actually going to be really useful in calculus 2 as well, if you recognize that easily. So why was this useful? Well, we can now rewrite this first one, x squared over x is just x. And then the second part, let's rewrite this as x to the 1/2 over x to the 1. And now we can rewrite that as, so remember that when you're dividing, you subtract the exponents. So we have 1/2 minus 1. And remember, we have not taken the derivative yet, right? All we're doing right now is simplifying our function. So now we have x minus x to the negative 1/2. So all we did, this is the same function we started with, we did not take the derivative. So not to be a broken record, but just to again mention it, because I just have seen so many people go wrong on this. One example of how I see people go wrong is like, you're still kind of working on simplifying this, and then all of a sudden you're like, oh, the derivative of x is 1, and you just turn it into a 1. And that wouldn't, then like later, when you take the derivative of that, that would turn into a 0, and so that would actually give you the wrong answer. So keep the simplification step and the derivative steps separate. So what do we get for our derivative? We would take the derivative of x, and we know that that is just 1. And then for this part, we bring down the exponent. So we have minus negative 1/2 x, and then we have negative 1/2 minus 1. So altogether, that gives us 1 plus 1/2 x to the negative 3/2. And that would be our answer. So one last example. So let's see. Let's do this one. Let's say we have the function x plus 2 squared. So you can't use the power rule on, well, actually, so we'll get more into this later. And in this case, it coincidentally would work if you did this kind of the wrong way, but let's forget about that. Basically, you really are only allowed to use the power rule if it's just x to a power. And so what we need to do is we need to rewrite this by expanding it. So if we were to multiply all this out, we would get x squared plus 4x plus 4. And now we can take the derivative. So now the derivative of x squared, we'd bring down that 2 and we just get 2x. And then the derivative of 4x, so the derivative of x, remember, is 1 because the slope of a line is just 1. And then we multiply that with 4. And then the derivative of 4 is 0. And so this would be our final answer. All right, that is it for today. So tomorrow we'll do a little more practice with these rules, and then we'll also introduce some new notation. So one thing that we're going to talk about that we haven't gotten to yet is the second derivative. So we'll talk about that tomorrow. Yeah, that's about it. Thank you.